My name is Jiguo Cao. I'm a professor at the Summerfield University. Okay. Yes. Um, Today I'm very happy to give you an introduction about functional data analysis. Before I start, I just want to know, like in the audience, I know quite a few experts in functional data analysis. Can you raise your hand if you know functional data analysis? Okay, so around like 1/4. Okay, yes. Okay, yeah. So the organized committee wanted me to give you an introduction. So I assume this will start from the beginning. Okay, so please feel free to stop me if you have any questions. And so this is coming from a short course about the functional data analysis, which is given on 3 days. I don't expect me to finish all the slides. So I just want to give you brief ideas about this area. And I believe in the following days, we will have quite a few experts to talk about more specific details on the functional data analysis. Okay, let's start. So here is what's functional data. This is one example. This is to show you the number of eggs laid by 50 fruit flies over 25 days. Okay, so here each curve represents one fruit flies, the number of eggs laid by one fruit flies over 25 days. Okay, so basically here we have 50 curves. Okay, so each curve here can be viewed as one functional data. Okay, so this is you can see that this functional data, the feature is that they change continuously and smoothly. We expect the number of legs fruit by flies is kind of decreasing, but decrease smoothly over the time. So here, for this specific applications, we want to explore the modal variations about these fruit flies. We want to see what's the difference among these 50 fruit flies over these 25 days.
Okay, question about the data.
Yes.
So, like in one day, like how many, like could you go over one curve? Like because they seem to be continuous, right?
Yes, it's kind of continuous. Yes.
But they don't lay eggs continuously, right?
That's right. Yes, but we feel that the observed eggs they laid is kind of will have an underlying smooth process. That's the assumption. Yes. So maybe the flies laid 5 eggs today and 3 eggs tomorrow, but like the underlying process we think generally is a smooth process.
Smooth.
Yes.
So it doesn't look smooth. You connect
That's right. But we will estimate the smooth curve be after this data. Yes.
So this is like you measure it once a day, right?
Once a day. That's right. Yes. Yeah.
Not every hour.
No. Yeah, once a day. Yes. Yeah. So each point here represents the number of eggs laid by one fruit flies on one day. Yes.
1 day.
1 day. Yes.
So on the second day, it's a new count. You don't add them. Right?
That's right. It's new count. Yes. Yes. Generally, the number of eggs is decreasing over the time. Represent the flies is aging over time. Yes. Okay. Yes. Yeah. That's a very good question. Please feel free to stop me again. Okay. So here, this is the functional data features. So they are often very complex. We can see nothing there. It's kind of fluctuation over time. And generally, we will have many observations per curve. We have 25 days observation for each of fruit flies. And we view that each of these curve is replicates our smooth process, underlying smooth process. These curves have very similar trend. So they are generally is decreasing over time. Represent these fruit flies is aging. Their reproducibility is decreasing over time. Okay. And again, the underlying process, we assume they are smooth process. Okay. Although we observed data is a little bit fluctuate over time. It's not continuous. So functional data analysis is basically the analysis of functions. Okay, so that's how the name come from. And the domain of the function, most times is time, but sometimes can be also space or energy. As long as a continuous time is fine. So in this application, we have 50 curves, okay? And so this 50 curves is a repeat measurements of a same smooth process. And also here, because of this curve is complicated, it's very hard to describe by some mathematical formula, like it's not a quadratic function for sure, right? And so there's a variations among these curves. It's hard to describe uh, just from eyes. So this is the summary we just mentioned, okay? So functional data analysis is a pretty hot topic nowadays in statistics. Generally, for each of these top journals, there will be at least one paper on functional data analysis. And there's many public software available and many applications nowadays. Okay, and but this area I find it's a very good area if you want to work on statistics because it's generally easier, I think, published compared to other traditional statistical area. So the prerequisite is also pretty simple. You just need to know multiple linear algebra. Basically, you need to know matrix. You can work on this. So these are the 5 classic books on functional data analysis. My talk is recorded. So you always feel free to see the recorded videos if you want to know these books. Okay, they are pretty good books. So the books I recommend to start is actually is this fourth book, Functional Data Analysis with R and MATLAB. And so it's a very small book with 100 pages and very easy to follow. They put the code in both R and MATLAB in their book, so it's very easy to follow. And there's some online resources you can use. So I have a YouTube channels called Functional Data Science. So basically, I put all my recorded when I teach functional analysis as a course. I put my recorded lectures there. So you can check there. Is many overlaps with my talks today. And we also have many FDA packages in R, public available. It's free. Okay, so so there's some more applications like functional data. So this is to show you one more applications. So basically, this is to show the temperature, average temperature in Vancouver. Okay, so here the temperature is kind of look like more smooth than the number X laid by the fruit flies. Because we have like a very accurate measurements about the temperature. And we also have the precipitations every day in Vancouver. And so this is have larger variations over the time. There's some data, like this is another application. This is to show the height measured for each kid over their age, like from age 1 to 18 years old, okay? So for this data, I want to show you that sometimes the observed time points are not equally spaced, okay? So basically for this data specifically, they only measured like their heights every year from age 4 to age 14. And they have like every 4 measurements, every quarter, every 3 months between year 1 to year 2 because they grow very fast in that period. So for functional data, it's very easy to handle the data are not equally spaced. Okay, so that's the one advantage to using functional data because we treat the data as the functions. So many of you have worked on splines. So using the splines as the tools, it's very easy to represent these functions even the data is not equally spaced. So this is another applications. So this is to show the body fat percentage for girls. Over time. And so in these observations, I want to show you this application because like for each girls, we only have their observations like a couple of measurements for each girl. So basically, on average, we only have 6 measurements. Okay, so this data we call it sparse functional data because compared to the temperature I showed you before, for each individual curve, we only have less observations. Okay, so this is called functional data, sparse functional data, and we are still able to recover the underlying functions behind this sparse data. Okay, so for this data, we want to look at the estimate the underlying functions. We also want to estimate the derivative of the functions using the using splines. Okay, so this is the data we recovered. So you see here for this ID 160, we only have 3 points, right? And we are still want to estimate the underlying functions. And so we also want to estimate their derivatives, okay? So there's a technique called a functional principal component analysis. We are able to recover these curves and their derivatives generally pretty accurately. The secret is that we want to pull all the subject data together and we will have more information. Yes. Okay, so this is the kind of some assumption in functional data. So basically we have to assume that the data coming from a smooth process. Okay, and also the process has to be not be easily parameterized. Okay, and we cannot write the mathematical formula for the curves. Therefore, we are using the spline generally to represent those functions. And there's some repetitions on the process. We have multiple curves, and the data don't have to be equally spaced. So some common applications on the functional data, including, for example, the EEG curves, right? And also the blood pressure we measure every year when we do the test. And also, for example, the virus in the patient bodies over the time. And also, for example, we also can see like the animal populations observed every year. And we also have environment like the weather data, air pollution data as well observed over time. And so for the economics or marketing, we can see the stock market, the stock price change over the time. And for the web data, we also can see the Google Trends or the auction price observed over time. Okay, so you can see there we have many applications on this functional data. Therefore, it gains a lot of attention these days.
Would you give examples where it does not apply?
Sorry?
You give examples where your theory would apply, but what are counterexamples where one should not use?
What the function doesn't use, right? Okay, that's a very good question. Yes, yeah. So when the function data cannot be used, okay. So basically, if you have only one measurement, only one with on one time point, that's the many traditional statistics. Like for example, if we look at the relationship about the mother's height compared to the children's heights, right? So each children you only have their height when they become adult, and you also have their mother's height. So basically, you only have 2 points, 1 point for each individual subject. In that case, you cannot use the functional data. Yes. So as long as if you just have one time point observation, you cannot use the functional data. Yes. Okay. Yeah. There's also many other things. For example, if the process is not smooth, you cannot use the functional data either. Okay. Yes. For example, like let me see. The rain data you can still treat as a smooth data. Let me give you some more extreme case.
Since somebody making mistake, the data sets are swapped. Then it's all changed.
Right, like some like a point process, for example, like we collect we observed the number of number of people infected by certain disease every day. Like sometimes if the number of people is a small number, like today you observe 5 people, next you may observe 10 people, maybe that kind of a more point process. That in that case, it is a little bit tricky to use the functional data. Yes. Yeah. Okay. That's a very good question. Okay. So you see here, most functional data actually are time series. Okay. So this is a common question people ask me, like, what's special about functional data compared to traditional time series analysis? So time series analysis is a more classic area in statistics. Okay. Basically, both data are working on the data collected over multiple time points. Okay. So the difference is their technique are different. Okay. So in time series, they assume the data are equally spaced. So you have to observe the data every day. Okay. You cannot have missing data on 13 days. Okay. So, but for functional data, don't have to be equally spaced. Okay. You can have data like, every day, and then you miss some data in 13 days, it's fine. Okay. And so for time series, they also assume that they have a constant mean. Okay. That's called a stationary time series. And in functional data, we generally will assume the mean changes over time. Okay. And so for time series data, we generally they want to have like very look at their correlations between the previous day and the current day. And so from functional data, we instead we look at this as continuous functions. Okay, and for time series, basically they want to do the prediction for the future time points. Okay, so for functional data, generally we don't do the prediction on the future. Okay, so we generally will look at the relationship between like some multiple variables, like we predict yt based on x of t instead to predict xt on the future time points. And for time series, it's very hard to dealing with missing data. For functional data, it's very easy to deal with missing data. So if you have time series with many missing data, functional data is a good choice. Another very, very big area in statistics is called longitudinal data. From the name, you can see that they also deal with the data observed over time. Okay, so what's the difference between these two areas? Again, their methodology are different, although the data points are pretty similar. Okay, so generally for longitudinal data, they give a summation about the process. Generally, they may assume that the data follows like a linear trend, is a linear function of t, or some like nonlinear longitudinal model. They were using like a unit, put some quadratic terms. Generally, they will give a mathematical formula in terms of the time here. But in functional data, generally, we will assume that there is no parametric assumption on the function at the functional time. Okay, and so in longitudinal data, they generally will look at like between subjects, within subjects variations, and also this is hard to deal with the missing data because they treat the time points as the covariates in the models. But here in functional data, it's very easy to deal with the missing data. Okay, so this is just to give you some rough ideas between the difference between longitudinal data and the functional data analysis. Okay, so here is a summary about the general feature for functional data. So basically, functional data are dealing with curves, images. Images can be looked at two-dimensional functions or multi-dimensional functions. Okay, and the functional data generally they assume the underlying function is smooth and they estimate the function as a non-parametric functions using splines. Okay, and so here I'm going to show you some more classic tools used by functional data. So before I change to the topics, any questions generally? Okay, it's good. Okay, so now let me go to functional PCA. Okay, so like for functional data analysis, there's many new methodology, many methods, but the key methodology they use many times is called a functional PCA. So if you know functional PCA, basically you can do functional data for most times. Okay, before I go into the detail about the functional PCA, can anyone raise your hand if you know PCA, principal component analysis? Okay, wow, majority of people know PCA. Okay, so so hopefully if you don't know PCA, hopefully you can still follow these slides. This is I make it a very as simple as I can. And also, I feel that this formula is much simpler than the Splines formulas, believe me. Okay, so the PCA, the general idea for PCA is to doing dimension reduction. Okay, so this is just to give you the basic assumption, the demonstration for PCA. Basically here on the left side, we have some circles, right? These circles represent a two-dimensional data, right? So we want to do a dimension reduction. We want to reduce these circles from 2 dimension to 1 dimension, okay? So in order to project this data to 1 dimension, the idea is that we want to find the direction where this circle show the most variations, okay? So if you look at this solid line here, this solid line represents where these circles show the most variation in this direction, right? You look at that direction, okay? So therefore, if we find this direction has the most variations, then we will find this direction, and then we will project each two-dimensional circle to this solid lines. Then this projection will become 1 dimension on these solid lines, okay? So these projected points will become 1 dimension. We can call this as scores or features about these two-dimensional circles, okay? So this is the general ideas about PCA. So basically, you want to find a direction where the data show the most variations, and then you do the dimension reduction, do the projection. Yes. So this is the idea for PCA. For functional PCA, the idea is similar. So basically, what we do is that we want to find these directions, right, where the data show the most variations. So the direction here we call it FPC. Okay, I represent by W1T to WKT. Okay, so this FPC represents the direction where this data show the most variations. Okay, generally the number FPC, the capital K, is very small. Generally, we just using 2 or 3 FPC is enough to capture the most variation about these curves. I will show you one example shortly after. Okay, and so after we find these top FPCs, we will project the curve XIT on this FPC WK of T. Okay, so then each of these curve XIT can be written as a linear combination of these FPCs. Okay, so the coefficient between the WK of T is SIK. Actually, is the score, is the projection of the curve XIT on these LPCs. So, after we doing this, and we actually have a dimension reduction. So basically, we have this XIT original curve is an infinite dimension functions, right? But after we doing this, find this WKT, this coefficient SIK will represent the curve now. So we only have, for each curve, we only have capital K number of scores. This small s represent the features about these curves. So this is the dimension reduction on these curves. Okay, so remember this number of LPCs is a very small number, like 2 or 3. So each curve will project to a 2 or 3 dimension. So we will have a huge dimension reduction using the functional data, functional PCA tools. So now let me give you one example. So this is, again, this is the data I showed you originally. So this is the number X laid by 50 fruit flies over 25 days. So basically we have these 50 curves, okay? Very complicated, right? And hard to see any variations, okay? And here we want to explore the variations among these curves. Maybe we want to do some classification, clustering about these fruit flies, right? We want to see how the fruit flies is different to each other, okay? So this is a general process we want to do using FPCA, okay? So basically we will have this N curves, right? And so first we will remove the means, okay? Because we only look at the variation among these curves. The mean doesn't matter. So we will remove this mean. So basically we find the average about these N curves is the mu of T. and then we will minus this mean mu of t. Okay, and then after we get this d-mean curve xit, and then we suppose we find this first LPC w1 of t, then we will project this curve to on this w1 of t. Okay, so we know that in functional analysis, the projection is basically is the product of these two functions, and then we do the integral, right? So this is the how we define the inner product in functional space, right? So basically, SI1 is the inner product of xit with w1 of t. Okay. So what we want to do is that we want to maximize the variation about these LPC scores. Okay. So since here these scores had mean equal to 0, so the variation of these scores actually equal to sum of the summations of these scores. Okay. So basically we want to maximize this sum squares of these scores subject to this LPC had to be length equal to 1. Okay, so this is our criterion to find this W1 of t. We want to maximize this variation about these scores. Okay, so any questions so far? Is this good? So this is the general formulas behind this LPC. Okay, so
you had some assumption from this W function?
it's the general functions. There's sorry, very general. No assumption on this W1 of t. Yes. So generally, this W1 of t will be estimated as a linear combination of the B-spline base functions. That's what we usually do. Yes.
So how to find W1?
So W1, basically, we will write down the W1 as a linear combination of the B-spline basis functions. And then we will estimate the coefficient on the B-splines by maximize this. Okay. Later on, I will show you actually there's a there's no model. What's the model? Yes, yeah, that's the only assumption. Yes, yeah, we have to do some assumption, right? So when I say there's no assumption, I mean there's no assumption on the parametric form of this W1 of t. We don't assume the W1 t is a polynomial function or quadratic functions. We only assume this W1 t is a smooth function. Yes.
You could not have say phenomena where say piecewise polynomial is not the best, maybe you would consider exponential functions for your W or so?
Using exponential function? You know, if you use the exponential functions that's kind of a parametric assumption, right? So if, in many cases, this W1t may not be follow the exponential function, for example, right? Yes, yeah, so we want to make the W1t to be flexible. Yes, that's why we like splines. So splines, you know that it can be approximate any functions, right? Yes. Sorry? Yes, L2 norm. Yes, this all work on this L2 norm space. Yes. Okay, so this is the first LPC. The second LPC is similar. So basically, we want to find the W2 of t. We will do the projection of xit on the W2 of t. We get the scores on the second LPCs. So here, we want to maximize the variation of these LPC scores. Basically, the sum of the summation of the scores and subject to the length of W2 equal to 1. And also the W2 of t had to be orthogonal to W1 of t. Okay, yes. So this is the general criterion. So the W2 of t represents the second strongest and most important modal variation among these curves. Similar, we can observe the rest top LPCs. Okay, generally we only have we need to a few, like 2 or 3. Okay, so these LPCs are orthogonal to each other. So this is a very important features for LPCs. So now we will project this xit to this LPC score. So therefore, we have a huge dimension reduction. So let me give you the example result on this fruit fly data. So remember, we have a very complicated 50 curve, right? So these are the LPCs we obtained from these 50 flies of curves. So you see here, this LPC1 and FPC2 has a very simple trend, right? I didn't give any parametric assumption. These are estimated by using B-spline functions. And this explained over 91% of the total variation among the data, okay? So you can understand that these two splines, two LPCs represent over 91% of information from the functional data. Okay, very simple trend. And so let's look at this each of these LPC scores individually. So this is the first LPC. This is like looks like a quadratic function, right? Very simple. And this is planned around 62% of total variations. Okay. And so when we do the data analysis, the key things we want to do is that we want to explain the result to the scientist, right? They want to, you will make sure they understand. You said this LPC is a very good feature, dimension reduction. But when you do the dimension reduction, what's this space, new space represent, right? I explain that to the scientist. So I will see the LPCA has a very good advantage that the LPC actually pretty easy to understand. So let me show you for these applications. For example, here, for the LPC1, you see here, it's kind of going up and going down, right? But overall, this LPC is positive over the whole time interval, right? Yes. And so basically, you can look at these scores as the integral of this W1T times Xi of t, right? When you see the integral, basically the integral is the average of the product of W1T and Xit over the time, right? So in other words, this W1 of t is just the weighted average. This LPC score is just the weighted average of the whole curve Xit, and the weight is this W1 of t, right? Yes. So therefore, for the first interpretation for the first LPC score is the weighted average of the number X laid by 50 fruit flies over 25 days, right? And this weight is given by this LPC. So it put a bigger weight around day 10 and less weight on the boundaries. The reason, if you look at these 50 curves, you see here on the day 10, these 50 curves show the maximum variations, right? Therefore, it gives the maximum weight here, right? So this LPC give you the optimal weights such that the LPC scores have the maximum variations. And the issue of this LPC score can be understand as the weighted average of these curves, weighted average of this total X. Okay, so this each LPC score represents the overall reproducibility of these fruit flies, right? Over their whole life. Okay, so this is the first LPC scores. So this is the second LPC scores. It's a kind of looks like a simple trend, but if you look at it carefully, it is a negative between day 8, positive after day 8, right? So if again this second LPC score SI2 can be looked at as the weighted average about these curves, and the weight W2T is negative before day 8 and positive after day 8. In other words, before day 8, the curve get a negative weights. After day 8, the curve get a positive weights. Therefore, this second LPC score can be understand or interpreted as the change of the X later after day 8. Okay, so basically, this second LPC score represents how quickly the decay of the reproducibilities of the fruit flies. You know, for example, if one fruit flies lay lot of eggs before day 8 and suddenly drop their number of eggs laid after day 8, they will get a very big second LPC scores. Means their reproducibility decreases very quickly. Suppose there's one fruit flies have a very flat number of eggs laid over days, then they will have very small second LPC scores. Okay, so you can see that this second LPC score can be looked at as the change of their reproducibility over time. So therefore, you know, this interpretation is actually pretty easy to understand. So the good news is that for most applications, I have working on like probably over maybe around 100 applications. For 90% of the applications, all the LPCs, first or second LPCs, they are all looking like this trend. Okay, I don't know why. Like, you know, they always like a first LPC is like always positive Okay, so it means that the first FPC score can be always viewed as a weighted average. Okay, and the second FPC can always negative at the beginning and positive after some time, and I can view it as the change of the curve over time. Okay, I don't know, I still don't understand why. Maybe mathematicians can give me some proof behind this, and yeah. So therefore, when we do the interpretations, we can always follow these ideas. Yes.
So I think if we view functional data as a way of dimension reduction for the analogy respect to PCA, dimension reduction for non-functional data. So in the dimension reduction field, there's also that non-negative. So that's why feel like that equals 4 and also to ensure both of them are
right.
That way you, I think, sacrifice the
That's right. Yes. That's right. Yes. Yeah. Non-negative components. Yeah. This is very good questions. Yeah. So like I also aware about this dimension reduction tools, and as far as I know, there's no current tools like using this positive that's called like one-way matrix decomposition, right? Yeah. So I didn't aware anyone doing that on functional data. This is very good ideas. Yeah. So for functional data, when we do the dimension reduction, there's many tools actually available. So there's also some nonlinear projection, like I saw people using like autoencoder, and also people using like neural networks to do the dimension reduction. Yeah, so there's many things we can do, but FPCA is kind of like a fundamental tool used because of these easy interpretations. Yes, that's yes, exactly. Yes, yeah. That's right. Yes, for sure. Yes, that's very good comments. Yes. Okay, any other questions? Okay, it's good. Okay, so I want to not show you the details about this, how we calculate these LPCs, but the general ideas is that actually when we estimate these LPCs, the fundamentally we can estimate these LPCs by solving eigenequations very in one step, got all these LPCs. So it turns out that somehow these LPCs is the eigenfunctions of the variance covariance matrix about the curves. Okay, so this is how we do this, and I will not show you the detail about the algebra, but it's basically we are doing the eigen decompositions. Let's look at one application, another application here. So this is like 35 daily temperature, average temperature for 35 Canadian cities, and we want to do the FPCA on these 35 curves. Okay, so this is the original FPCA. If we do the eigen decompositions, okay, this we got here. Okay, and so you see here, when this we look at this LPC, each of these curves, these have this like a small variations, small like bumpies about these curves. Okay, this is not helpful when we do the interpretations. So therefore, basically we want to have a kind of more smooth version about these curves. Okay, so how can we do this? So the basic idea is that we want to get a roughness penalty, like when we're using the smoothing splines. Okay, so we will get a second derivative on the LPCs so that we will get a smooth version of these LPCs. Okay, so this is the general ideas. We do this PCAs. Okay, so again, here you see here for the LPC1 is generally is this black curve is positive on the whole time period, right? So we can see that this first LPC scores is generally the overall average temperature, and for the second LPCs is this blue curve here. Basically, it's a negative in the summer and positive in the winter. So we can see that LPC2 as the relative temperature of winter compared to the summer. Okay. Yeah. So like after we get these two LPCs, then we can project all these curves to a two-dimensional space in the LPC space, right? So basically here we have these 35 cities. Each of the city corresponding just two scores, right, on these two LPCs. And therefore, we are able to project all these cities to a two-dimensional space, and then we can do the clustering on these cities, right? So now it's much easier if you want to do the clustering. And you can do further analysis for sure. And so this is just to show you one benefit to use the LPCA. You can suddenly do the dimension reduction. Okay, so this is a kind of a summary about the functional PCA. So basically, a functional PCA is a very good tools if you want to doing dimension reduction on the curves, and you want to explore the variation among these curves. And you can also, after you get these features, you can put them on the further modeling ideas. Yes, questions? Yeah.
Well, my question is, your size of each data, the curve 25, right?
Yes. Yeah.
What happens to data sets of different size?
Yes. Yeah. So if data is a different size, we can still do it. Recall that when we do the FPCA, the key calculation is that we need to first find the variance correlation matrix about these curves, and then we do the Argand decompositions on this.
The mean is the average. The average has the same size.
So not necessarily. So when you look at, for example, if you want to calculate the mean curve, right? So what you can do is that you can project all the individual data on together, okay? And then basically you will have kind of some clustering points over the time. Then it's very easy to find the mean functions. Yes, that's the general ideas. And to pull all the individual data together. Yes. Yeah. Okay.
I know.
Yeah. Yes.
I have two questions. The first one, when you smooth the FPCAs,
Yes.
do they still remain orthogonal or not after the smooth?
This is a very good question. So depends on how you do the assumption, but generally when we do this is our constraints that the length of the W2T you see here is the W2T now is not length equal to 1, right? It has this derivative here. And also for the orthogonality, we also have an extra the second derivative here as well. So they are not like strictly orthogonal anymore. Yes. Yeah.
The second question is like surface.
Sorry?
Is it possible to do this with surfaces?
Like, for example, we have two-dimensional functions. Yes, we can do that. So there's a method they call a two-dimensional FPCA. Yes, we can also do three-dimensional, multi-dimensional function.
When you do two-dimensional, what these splines do?
When we do the two-dimensional, we will using the Bernstein polynomials bivariate splines. Yes, that's our favorite tool to use. What kind of partitions? Triangulations. Yes. Yeah. That's our favorite tools. Yeah. Degree of freedom generally we will choose in second derivative as a smooth penalty. Yes. Yes. Yeah. Second derivative. Yes.
I think degree 2 is C0, C1. Quadratic.
Yes, quadratic functions.
So locally they're not C2, but globally you could have C2 and the polynomial C2. If a triangulation fine enough, there are lots of C2 functions in quadratic. Think about the quadratic polynomial is C2, C infinity.
Yes.
The space is not empty. So they just use it.
Yeah, Professor Lai actually is, if you have any question about this Barrett splines, Professor Lai is definitely expert. We are so glad that Professor Lai developed these very nice tools for the Barrett spline we can now use directly for the when we do the two-dimensional or multi-dimensional FPCAs. Yes. Yes. Okay. Any other questions? Yes.
Yeah, just to answer a bit of the first question, on variable domain, there is some work on variable domain functional principal components, which is exactly the question where the length of your curves are not the same.
Can you see? Okay, so what's the name again?
Variable domain functional principal components.
Okay, that's cool.
It's mostly done with data, for example, from the smartwatches.
Okay.
So there's a lot of work already going on.
Okay, that's cool. Yes.
And then the second point about the BIRS.
Yes.
More on Wednesday.
More on Wednesday. Okay, that's good. That's good. Okay, that's good forecast. Yes. Any other comments or questions?
Still, I don't understand which kind of function you use in the bivariate case.
Sorry?
Still, I don't understand which kind of function you use in the bivariate case.
Bivariate case, right? So, for example, like one application I'm working on is to work on the image analysis. So
Yes, but the approximation phase, so your principal component is one.
it's two-dimensional functions.
Yes.
Yeah.
Which kind?
Work is we using the bivariate splines. Basically,
Which bivariate spline?
is you basically you estimate as let me see. I can show you quickly. Like here. Yeah, we can discuss this later. Like we work on this two-dimensional space. Basically, we're doing the image analysis. We will use this two-dimensional FPCA. Yes. Okay. Any other questions or comments? Yes.
Thousands, hundreds, huge number of genes and they are collected on
Okay. Okay. Yes. Okay. Okay. Yes. Yeah. Yes. Yeah. So if you have data collected over the spatial locations, can be two-dimensional functions. Yes. Okay. So before we run out of time, I want to show you the last topics, very important topics in functional data analysis. I feel that this is a kind of like, you know, the last things you need to know about functional data analysis, they call it functional linear models. Okay. So, you know, functional linear regression models is the fundamental tool used in statistics And for functional data analysis, we also have a functional version called functional linear models. Okay, so I want to just give you a very quick introduction about the functional linear regression models. Basically, the special thing about these functional linear regression models is that we at least have one variable as a function of time. Okay, so for example, here we have 3 different scenarios. First, we have the covariate is the functions, xi is the covariate is the function of time, and we have a scalar response. Yi is just a scalar variables. Okay, the second scenario is that our covariate is a scalar and our response is a function. Okay, so we will do the regression of yit on the xi. And the third scenario is that we have both the covariate xi and the response yi as a function of time. Okay, so these are the three scenarios about the functional linear regression models. And I will only give you an introduction about these first scenarios. The rest will be very similar. Okay.
What is the response?
Response is this y. Y is the response. Yeah. So like in statistics we will treat like the response means like what do you want to predict, for example. Like for example, if you're using children's height to predict using the mother's height to predict the children's heights, then the children's height will be the response, and mother height will be we call it covariate. Okay. Yes. Very good question. Okay. So so here this is one example. For example, like we want to predict the annual precipitations based on the daily temperature. Okay. So the response is the annual precipitation. We just have one number for each city for 1 year, and we will have a curve for each cities every basically we have the daily observations of temperature for each city. Okay, so this is the one application we can do. Okay, so what we can do is that basically for general linear regression models, we will look at the temperature every day as the predictors. We will predict the annual precipitations, the yi here, using these linear regression models. Okay, the problem here is that we have too many temperatures. We have 365 temperatures for each city, right? So therefore, this coefficient beta, we have too many betas. Okay, so in other words, this is we call the collinearity problems. So basically, this beta is not identifiable. Okay, so what we can do is that instead of to write this as a summation in functional data model, we will write this xi because it's a function now, right? Function of t. We also represent this coefficient before xi of t, the beta as a function of time, right? And then the product of this beta t and xi t will be just the integral of the product of beta t times xi of t. Okay, so this is called a scalar on function regression. Okay, yes. So now the idea is want to estimate this beta of t instead. Okay, so how we do this? So basically the idea is we want to do the least squares. Okay, we want to minimize the distance of yi with the right side of the equation. We want to estimate this beta of t. So what we generally do is that we will represent beta of t as a linear combination of the B-spline basis functions. Okay, that's the kind of the tricks we use all the time. Okay, so we will represent beta of t as a linear combination of this phi j of t. Phi j here we call it basis functions using B-spline basis function generally, and we will estimate the coefficient on the basis functions. Okay, and so we have this morning we have many detailed talk how to come with the basis function. Basically, we are using either Fourier basis functions or B-spline basis functions. Okay, our favorite cubic B-splines, and I will not give an introduction here about the splines. And so after we get these representations, we can plug in this beta of t and the linear combination of basis functions into the equations, and then basically this phi of t, the basis functions is known numerically, right? And then we can get this product of phi t with the xi of t numerically. We can get this integral, And then we will know this is Zi now, right? Zi is the integral. And then we can estimate this C, the basic coefficients by using the least squares. Okay, this is the general ideas. Okay, and so, but the estimated functions can be pretty bumpy. It's hard to interpret. So what another trick we will do is that we will add a roughness penalty on the coefficients beta of t. And now we can get a more smooth functions on the beta t. So it's still linear. So this is kind of what the result to show you if we add the roughness penalties on the beta of t. Okay, so I think I covered most of the, going very quickly, but I've covered most topics, important topics on the functional data analysis. So I know in this workshop we have several very good FDA talks, and you will hear more detail about FDAs. So if you have any questions, please let me know. Okay, any questions? We have 3 minutes. Yes. How do I choose lambda? This is very good questions. Okay, so this is always tricky. Okay, and so the general idea is that so because of this basic coefficient C, generally is a linear function, linear projections of the data Y. Okay, so therefore we can define the effective degree of freedom as the trace of the height matrix. Yes. So after we got this effective degree freedom, we can define a GCV, and we can choose the smoothing parameter by minimize the GCV. Okay, or using BIC. Okay, or you can use cross validation as well to find the optimal smoothing parameters. Yes, very good questions. Okay, any other questions? Yes.
So you use it's not that you use often B-spline.
Sorry.
You use often spline and B-spline.
B-spline, yes.
B-spline.
Yes.
But so how do you choose the nodes?
The nodes, the general idea is that we call that we are using a saturated number of nodes. So in other words, we will have set the number of nodes equal to the number of time points with the observations. For example, for our fruit flies, we have 25 days. We will put 25 nodes. And then we were using this roughness penalty to control the smoothness on the estimated functions. Yes, that's the general ideas. Yeah, but if you have Spline better than me, if you have better idea, let me know, and I'm happy to try it. Do you have?
You also mentioned that the main point here is that you can treat the data that are not equally spaced, right?
Right.
So if you have a large variation in the spacing of the data,
Yeah.
do you recover this variation with the node of the splines or not?
No. So generally, like we don't choose the location of the nodes carefully. So we will like pretty arbitrarily to choose the number of nodes and their locations, and then we will using this roughness penalty to control the smoothness. That's the general ideas. Yes. Yes.
How beginner question is how difficult and is it useful to go beyond the linear?
That's a very good questions. So you can see here for both the FTCA, FTCA generally you can treat it as a linear projection, right? And for the functional linear models, it's also a linear assumptions. Yes. So this you have very good questions. So why not we go beyond the linear relationship? So the answer is yes. Sometimes it's useful to go beyond the linear by using multiple linear, nonlinear models. And if you have enough data. So now, especially after this deep learning and neural networks so popular. So, for me, I treated the deep learning or neural networks as very good tools if you want to model nonlinear relationship. So people already have done that, have tried that. So we have one review paper called statistical learning for functional data. So it reviewed all this nonlinear approach on the functional data analysis. You can take a look. Yes. Okay. Yes. Hello. Yes.
Organisms experiments is a research which in many cases shows that how much some
So how can we know that the results are good? Yes. Yes. So how do we evaluate how well the method is? I guess the key assumption, the key for me, I think the key criterion is that how well you can do the prediction, right? So if you have, suppose you have some training data and test data, if your method work using the training data, it had to working for the test data as well, right? So I guess like when we do the method comparison, we also will look at their prediction errors. Yes.
Errors experiment or errors estimated.
So not theoretically, we generally, there's a very limited series in data analysis. We generally will numerically do the comparison. Yes. Yeah. Sorry?
There's also theory functional.
Yes, there's also series behind that as well. Yes. 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 Mm. I believe so. Yeah, I think that some people already done that. Yes. Yeah. Yes. Mm.
So if yeah, questions, we thank the speaker and
Okay.
the audience for the discussion.
Thank you. Yes.